All right, good afternoon, ladies and gentlemen, and welcome back for those of you who are here this morning. We're very pleased to welcome you here, and we have a very exciting panel lined up for you this afternoon. It's on the need for innovation in energy storage. And I will stop there. I'm going to turn the podium over to Dr. Jatin Nathwani. He's our Executive Director of WISE, and he will be moderating this panel as well. Thank you very much, and hope you enjoy it.
Thank you, Tracy. I think it's become self-evident, certainly over the last 5 or 7 years, that energy storage is a critical component, enabler, make or break, if you wish, if the energy system is going to transition to one that is renewables based, that has a characteristic of intermittent generation, variable generation. So storage will have to play a key role, and so therefore innovation in the field of energy storage becomes a very important aspect of where we may go in the future with our power systems. And so that is why we've chosen this subject. It's very timely, it's topical, and it is important. I have an excellent group of panelists here whom I will introduce briefly as we go through the list, but thank you again for coming. So we will begin with our first speaker is Professor Chen. He's a professor here in the Department of Chemical Engineering and Director of the Applied Nanomaterials and Clean Energy Limited. So Professor Chen, please.
Thank you so much. And it's a great honor to have the opportunity to introduce our work on the rechargeable zinc battery here. And since our panel topic is energy, right? Definitely, we will mention energy is critical in the next decade. And because we have more and more people, right? And as you can see here, the top one problem that we are facing in this century will be the energy. So since energy is important, the majority energy that we are using actually is in the form of the electricity. So then talk about the electricity, we have to talk about our grid. So for the grid, the current stage, so today's grid, it's more like this. So from generation to transmission and distribution to the home. So mainly it's only one direction. And until between distribution and home, there is feedback. So this is today's electricity grid. Then for the electricity grid, there is a lot bigger chance for us, because at the current stage, we need more and more electricity. So we need more electricity grid. So in North America, especially even U.S. alone, in the next 50 years, you need $80 to $150 billion will go to the electricity and grid, right? And also with the time, we will because at the current stages for the electricity, when we try to use the electricity in the during the delivery, will have big loss, 8 to 10%. So for in order to improve the electricity efficiency, we should try to go to the BET, or we call it a smart grid. So what's the smart grid? So this is a schematic of smart grid. This we call it the next generation grid, or you can say it's tomorrow's smart grid. So for the difference between this smart grid will be there is more feedback, right, between each system. From the generation and the transmission, you have the communication between them, each other, and also between transmission and the distribution and the home. Especially, we have another system which is introduced, which is renewable energy with the electricity transportation system. So this is the different. If you take a look at the smart grid, the difference between tomorrow's smart grid and today's electricity this smart grid have another component, important components, and also you have more communication among them. So that's this smart grid. So for the smart grid, with tomorrow's smart grid, it is expected that we can reduce the carbon dioxide emission greatly. And also, we hope it will expect to save a lot of money when we try to use it, because it can improve the energy efficiency, right? And also definitely, by using the smart grid, we expect we will pay less, smaller bill, right? Lower bill. So with this expectation, for the smart grid, if we go to our local area, like this is Toronto Hydro. So since 2008, they plan to invest has invested $1.3 billion into the electricity system, and definitely in the North America even big. So for this one, for the smart grid, one of the biggest challenge I would say it's dealing with the energy storage. So for each section of the smart grid, we need the energy storage system. Especially when you go to the substation scale or residential scale, we need a very good energy storage system, which is related to the battery technology, or the hydrogen technology. So in order to make the smart grid happen more efficiently, we have to find a very good, and low cost and high efficient energy storage system. So with this goal, when we talk about the smart grid, here this is actually the slide provided by the eChemie. eChemie, as you know, they demonstrated the first stationary, the energy storage system for the smart grid at local in Toronto. So as they claimed, for the smart grid system, if you take a look, this slide, the battery technology, so this battery will cost 60% of the total, smart grid system application. So which means if you want to make the smart grid widely available, you have to reduce the cost. Now at current stage, the biggest challenge is the high cost for the smart grid. And the biggest cost actually is from the battery, because they are using the lithium current commercial lithium battery technology, right? So with this challenge, we were thinking, beside for the battery is very important, right? And also talk about the electric vehicle, right? For the electric vehicle, also the biggest challenge will be the battery technology. Because for the electric vehicle, right, at the current stage, cost is very high for the lithium battery. And also the range, because the energy density of the lithium battery is still not high enough. So which means we need for the regular vehicle, we need 1 ton of the lithium battery. And also the range is not ideal. It's not good enough. And also you need a long time for charging, right? So charging the battery. So the fueling time is also a problem. And talk about the safety for the lithium battery technology. Now the safety also is still an issue, right? If you take a look at this slide, you see there is the combustion or explosion problem that when you use the lithium battery-based electric vehicle. You must have heard some news. Even the Boeing 787, right, at the current stage, in the past few months, you heard the story, because the Boeing 787 is delayed because of the lithium battery technology used in the airplane. So with this challenge, we take a look at this chart, So number one is definitely cost and also energy density. So talk about the energy density at the current stage for the energy technology. We have a electrochemical energy storage system. We have a supercapacitor, battery, and fuel cell. So fuel cell definitely has the highest energy density, but then followed by the battery, right? So if you take a look at this chart, these four are popular, commercial available battery technology, like lead-acid battery, nickel cadmium, or nickel metal hydride, and the lithium battery. So lithium battery is has the highest energy density battery among these commercial available battery, right? So, but if you take a look at the zinc battery and the lithium battery, they even have higher energy density that we expect. So because of this high energy density of this technology, so we, in the academia, also in the industry, we think that this technology will be the next generation battery technology in this world. So that's the reason a lot of research are focusing on this. So, but the question is, since this technology is so good, right? The energy density is so high, so why still not commercially available, right? There is a reason. So let's take a look. So before we take a look, the reason why it's not available. Let's go to the advantage of just the zinc battery. So for rechargeable zinc battery, the reason we think it's great is go more specific, high energy density. So if you take a look at this chart, the energy density is almost 5 times higher than the lithium battery. So which means with the same size, you can provide more power, right? The battery can last a longer time. And also, the lithium zinc battery compared with the current battery technology is more environmental friendly. For example, like lead acid battery, we don't like lead, right? It's energy environmental pollution. So compared with the current commercial technology, this is much environment friendly. And also low operation risk, because we are not using for this technology, we are not using organic electrolyte, not like a zinc battery. So which means we don't have the combustion or explosion problem. And also at the same time, the materials that we are using in the zinc battery is much cheaper. So compared with the metal cost, you see the zinc is only $2 per kilogram, but the lithium is $32 per kilogram, right? And also, especially in Canada, we have large zinc deposits, right? So we can use it easily. It's fairly available. So with this advantage, if we take a look, the previous question is why rechargeable zinc battery is still not available. So the main challenge, one of the main reasons is actually there is no commercial available catalyst for this technology. The reason is because if you take a look at this zinc battery, for this reaction, you need a bifunctional catalyst. The reason we call it a bifunctional catalyst because we must involve 2 reactions. One is during the discharge, there is an oxygen reduction reaction. So that is produce electricity. So when you charge in the battery, this oxygen reduction reaction need to be reversed. We call it oxygen evolution reaction. So which means these electron materials, or say the catalyst need 2 functions. You need to be active and high durable for both these reactions. Not like only the fuel cell is one direction, just a discharge. So that's the reason, major reason this technology is still not commercially available. And even this, precious catalyst, it's good, but the performance is still not good enough for this application, and even the durability is very poor. You will see later the performance. So our approach actually we developed in at Waterloo at our my group is we using the nanotechnology design. We designed the co-columnar structure catalyst. We call it a bifunctional catalyst. We hope to have excellent OER and OR activity and also stability. That will relate to the lifetime of the battery, right? So this is the catalyst we designed. We designed a co-columnar structure catalyst. And this catalyst, as we mentioned, will be good at ORR, which is discharge reaction. And also, when we do the charging, all this catalyst will be also good at OER. So we have two materials, but combined into this co-columnar structure by design, and hope this catalyst will have synergetic effect during the reaction. That's our purpose, right? So this is the catalyst that we designed. With this catalyst, actually, we successfully, if you take a look, the performance, you see for the discharge, is the same as the platinum. for the charging is much better than the platinum catalyst. So this is a very unique catalyst we developed. And for the charge discharge, if you take a look, for the platinum catalyst, after 70 hours, the performance, this battery died because the corrosion happened very fast. For the platinum, it's not stable in this system during charge discharge. But for our catalyst, you can see during charge discharge, after 1,000 hours, almost no degradation. So this is a great improvement and breakthrough. And with this technology, actually, this is our core technology. With this technology, we also, because we want to put this catalyst into the system, right? So we also, in our group, we designed a new type of electrolyte and also zinc electrolyte. Then combined together by the system design, hope to get the cell, good battery. And this is a battery actually we designed in the lab. This is the first generation is small. So the second generation, we go to the 500 watt at current stage. Actually, with this battery, actually we can, at current stage, we put into this electro scoot for demonstration, actually in our lab. If you go to our lab, we combine with battery management systems that developed in our labs and put into this electro scooter. Originally, when we get this scooter, it's powered by lead-acid battery. Now we are powering by the zinc battery, and it's under investigation. So this is our goal. And for this technology, we already developed several patents around it, including this unique catalyst and also other components of the zinc battery. And actually, our research office, actually Saeed is here. He is helping to try to do the commercialization. And we plan to open the collaboration and also try to get this company ready in the near future. So this and definitely we hope this technology could be used in the smart grid and also transportation like electric vehicle system. That's our goal. Thank you. Thank you for your attention. This is my group actually. Yeah.
Thank you, Professor Chen. And in case you missed the lab visits, but after this panel and you're interested in this battery research, you're welcome to visit the labs. Our next speaker is Rob Harvey. Rob is the Director of Energy Storage at Hydrogenics. And in this role, he works closely with utilities, regulators, and associations to define the business models and define the customer requirements for the power-to-gas proposition. Rob?
Thanks, Justine, and I really appreciate the invitation to speak at the WISE Energy Day today. There's not one size fits all with energy storage. We've heard about zinc air batteries, there's flywheels, there's super caps, and at the other end of the spectrum, there's power to gas, which is what I'll be talking to you about today. And to start off, there's two thoughts. In one respect, if you look at, this is a chart of the end use of energy. And all of the focus around the world, and most of the focus has been on renewables, has been in the electricity sector. And there's a good reason for that. The potential for renewable development is highest when you look at PV and solar and wind turbines, geothermal around the world. There's no question the highest potential for renewables is in the electricity sector. The challenge is that the electricity sector only accounts for 19% of the end use of energy. So all this effort, well spent, is going into 20% or 19% of the end use of the challenge. What about the other 80%? About 35%, this is Canadian statistics, 35% of the end use of energy is in natural gas, primarily for heating. Another 36% is for transport fuels. And while there's opportunities for renewables and sustainable solutions in both gas and transport fuels, they're fairly limited. There's not enough biomass in the world to create biofuels for the transport sector. And certainly when you start looking at the ethics of using crops for creating biofuels, even the amount of crops it would take to make a meaningful dent in the transport fuels is pretty limited. Power to gas is if you start looking at, well, what is your solution set or challenge set going beyond the electricity sector and looking, well, holistically, and I know much of the work WISE does is looking holistically as well. You ask the question, well, what if we said, well, the solution set is the electricity sector and the natural gas sector, just for a start. And if you could take surplus renewables from the electricity sector, store them in the natural gas grid as in natural gas, and then bring that back as renewable generation within the existing infrastructure for natural gas plants, doesn't that open up opportunity and options for it? And that, in a nutshell, is how can the essence of power to gas. How can we leverage the existing infrastructure, specifically the gas infrastructure, the pipelines, the enormous 80 terawatt hours of gas storage in the province of Ontario, and the existing infrastructure for dispatchable generation in our combined cycle gas turbine plants, the concept of smarter energy networks, and use that as a form of storage and a form of increasing the amount of renewables in the overall system. It brings flexibility to the power grid in the process. If you look at a simple definition and for power to gas, we're basically converting clean generation when we can't use it into renewable fuel, power, or heat where and when we can use it. And we're doing that by leveraging the inherent characteristics of the natural gas grid. In terms of energy storage, power to gas is the only solution that involves the transport of energy. Most energy storage solutions involve the capture, storage, and discharge of energy, but they're always in one spot. It's where the flywheel is located. It's where the zinc air battery is located. And for many applications, that's exactly what's needed. But when you look at very large-scale energy storage, the ability to transport that energy through the to transport that energy with the natural gas system is a big advantage. If you look on the left panel there, integrating renewables, the ability to capture surplus wind power and in Ontario surplus baseload power in the form of nuclear, clean energy when it's in surplus. The electrolyzer, you remember your high school chemistry, you run a current through water and you produce hydrogen and oxygen. And that's what we're doing. We're using a decades-old technology with some improvements I'll be talking about to produce hydrogen. And then the hydrogen can be used, the options for using that renewable gas are threefold. We can use it as fuel in jurisdictions like countries like Germany and Japan and California, where they're building out the hydrogen fueling infrastructure to introduce fuel cell electric vehicles as early as 2015. We can use it as distributed fueling stations. So where you've got the electrolyzer and have your power to gas plant, you've got a hydrogen fueling station. Another option is to inject it into the natural gas grid. As I mentioned, in Ontario, we're blessed with a very robust natural gas infrastructure, including 80 terawatt hours of gas storage. You inject the hydrogen, it mixes in the natural gas, and in effect, you're creating a portion of the natural gas system that is now renewable. And that gas can then be used just as it is today. It's much like the concept of bullfrog power, which you can buy green electrons, you can subscribe. Now, does Bullfrog guarantee that they're going to get you those green electrons that came from a wind turbine? Well, of course not. But the accounting for it and the market mechanism is there. The same is true with the natural gas grid. If we inject 2% or 5% hydrogen, renewable gas, into the natural gas grid, that's spread through the grid, and it will come out as it does today in used and dispatchable power. You've got a combined cycle gas turbine. If it's running on 5%, then 5% of that power is now renewable. The same is true for low carbon heating. If that gas with that hydrogen content is used in your home, a portion of that is now renewable. The beauty of it is we've taken a clean but sometimes with the wind power, intermittent resource that's not always when we need it. It may be at night, it may be seasonal changes. We've captured it, and now we're using it as a clean but dispatchable resource when we need it, coming through as heat or dispatchable power. The last application is using the renewable hydrogen in the production of liquid fuels. That's a refinery, so if you're producing diesel or petroleum, there's a lot of hydrogen that's used in the production of transport fuels. We're seeing this, a lot of interest in this in the EU, and in terms of even looking at directives that are being debated of, we recognize the limitations of ethanol and the ethics of food crops and land being used for that. But if you use renewable hydrogen in the production of diesel and petroleum, you're going to increase the renewable content of those transport fuels and have a very big impact on the carbon footprint of those fuels. Just to give you an idea of the difference in terms of the energy density of hydrogen is one of the important characteristics of power to gas. This is an example of the profile of a wind profile. I believe it's in northern Germany. I'll be saying Germany a lot. A lot of the activity in power to gas has been in Germany because they're facing the challenge of high penetration of renewables and integrating high penetration of renewables sooner than most other parts of the world. If you look at this as an example with a 2 million cubic meter salt cavern. And if you were to pump air into that salt cavern, and that compressed air energy storage is another technology, the rectangle on the bottom left there represents 4,000 megawatt hours. That's the amount of energy storage if you pumped air into that salt cavern. 4,000 megawatt hours is a lot of power. It's significant. But if you took the same space and injected hydrogen, you would have 600,000 megawatt hours of storage. And that's represented by that dashed rectangle there. So it's orders of magnitude more storage potential in the same space. And you think, well, why do we need that? You know, this is where it gets into one size doesn't fit all. I'm going to put a plug, if you haven't already seen it, there's an excellent power to gas poster out there advised by Professor Fowler and a team looking that Hydrogenics and Enbridge and others are working with to look at some of the characteristics of power to gas. And one of the one of the important characteristics is the size of the storage. Lost my point here. Size of the storage, but the other characteristics of looking at the process of hydrogen in storage and some of the characteristics in researching the movement of the hydrogen and how it interacts with other things as well. There's also a chart on that poster that talks about seasonal storage. If all you ever had to do with storage was to say, well, and you see a lot of the charts, peak shaving is a very important application for energy storage. So if you have a surplus of energy at night that you can't use, you store it at night, you bring it back during the peak during the day, that's peak shaving. The aspect of, well, what if it's longer than that? If you look at Ontario and the graphs that they have there, and I could have included the slide, but I was working with the stated limit here. In Ontario, in the late spring and early fall, we have days, consecutive days, where between the nuclear baseload, must-run hydro, and just an average amount of the wind, that we have surplus generation for 24 hours. And you have surplus generation for 24 hours and the next 24 hours. And if you're dealing with a peak shaver, like pumped hydro, well, the first day everything's fine. You fill up the reservoir, you absorb the power, and you've done your energy storage for night. Well, the next day you can't bring it back because you've got a surplus the next day, and the next day, and the next day. And you would need an extraordinarily large reservoir to store all the excess power that you have. That's the concept of seasonal storage, storing excess power in the spring and bringing it back in the summer. And the natural gas system is a very large sink that we can use seasonal storage. Another characteristic of an electrolyzer is that it's very fast. People don't think about it, but it's as fast as a flywheel. A flywheel is got a millisecond response to an input signal for either absorbing or discharging energy. This is a test that we did with the independent electricity system operator back in June 2011, and they provided a signal which is set in the green, and then the blue underneath is the response of the electrolyzer. So you can see that it's a very fast response. In the management of the electricity grid in Ontario, the IESO sends out a signal every 4 seconds to those that provide what they call frequency regulation to help do the fine-tuning of matching exactly the supply and the load in Ontario for power, and they're doing that every 4 seconds. An electrolyzer can provide that role while it's providing that storage as well. Give you some idea of what's gone on, and most of the activity, as I mentioned, with power to gas has been in Europe. There have been 30 demonstration projects for power to gas that have been announced today, and 18 of those are in Germany. And I mentioned Germany. Why are there so many projects in Germany? The whole concept of power to gas was developed in Germany to deal with the challenges of very high penetrations of wind. In 2012, 25% of Germany's electricity was provided from renewable sources, which is remarkable. And of the wind generation, the aggregate capacity factor for their wind fell below 20% for the first time. Now, a typical capacity factor for wind in Germany, is it because they don't know where to put wind turbines? Well, of course they know where to put them, is on the order of 33%. And it may be higher in some locations, but in aggregate over the country, it will be about 33%. So fully 50% of the potential capacity is being wasted, is being curtailed. And that's today. As they ramp up and accelerate the decommissioning of their nuclear fleet and add more renewables, that challenge is just going to be harder. So that's why the intense interest in seasonal storage and power to gas in Germany. We're working with providing the electrolyzers for 8 of those 30 projects and 4 or 5 of the very large-scale projects over a megawatt. This is the first. E.ON is a large electric gas utility in Germany. This is their Falkenhagen project, which is in northern Germany, and it's a direct injection application. This project was inaugurated in August, and there's been a lot of interest and visits to this site. It's a containerized solution with our electrolyzers, the alkaline unit for electrolysis. What you can't see is there'd be a metering and compression and interconnection with the natural gas grid to inject that. This is a 2 megawatt plant. It's a small scale demonstration project. Just quickly, some of the other applications I mentioned are also paralleled in Germany. There are applications for hydrogen fueling stations. There are applications for green compressed natural gas with biomethanation processes for working with anaerobic digesters to produce synthetic or biomethane for fueling. Audi is a company that's involved in that. They call it e-gas. There are also applications and demonstration projects for industrial hydrogen as well. Closer to home, we're working with Enbridge and the IESO and the Canadian Gas Association to do the first demonstration power to gas project here in Ontario. And the objectives are to demonstrate the ancillary services potential, frequency regulation, and potentially other services that are needed in the future, such as ramping with the IESO. It will be the PEM electrolysis. I'll be talking about the next generation technology in a moment, the proton exchange membrane for larger scale deployments and a contracting path. And then working with the Canadian Gas Association, particularly ETEC, their research arm, for setting gas interoperability standards and metering. There are no regulations in Ontario, and indeed probably anywhere in North America, for injection of hydrogen into the natural gas grid today. And I've kept it to the 7 slides. The one other comment I'll make just on the PEM electrolyzer. Saw the picture with 2 megawatts, and you see those are ISO 20-foot containers. You can imagine for energy storage, when you're talking large scale, we'll need 20, 40, and perhaps 100 megawatt sorts of projects, because at the times of surplus, you need a lot of capacity to absorb that surplus. You can imagine if you had, this is 2 megawatts, if you needed 40 megawatts, you're taking a lot of space. The next generation PEM electrolyzer is basically the size of a bar fridge. And a 40 megawatt project would fit on 60 meters by 25 meters in a building. So it is the platform, the technology platform we'll be using to do commercial scale power to gas projects. Thank you.
Thank you, Rob. We will come to the questions in the panel discussion. Our next speaker is Professor Michael Fowler, and given the the infrastructure of this room. He will be speaking from up there. In case you're wondering where is Professor Fowler, with slight limitation here. He's a professor in the Department of Chemical Engineering and a member of the Ontario Fuel Cell Research and Innovation Network, working towards overcoming the technical barriers around the full economic and technical potential of fuel cells. Thank you. Michael.
Okay. So I'm going to be talking about the cascaded use and repurposing of lithium-ion batteries from plug-in hybrid electric vehicles. Doing this research with Royden Fraser and Steve Young, and we have students Leah and Sean who are also involved in this. And this research is sponsored by Mitsui. So what we're actually talking about is when you look at a plug-in electric hybrid vehicle, you're going to be putting fuel into that vehicle and you're going to be putting electricity into that vehicle that comes from the grid. We're going to take the batteries out of that vehicle once the battery is finished in the vehicle and repurpose it so that we have it for electrical storage. And then we'll be taking electricity from the grid and putting it back into the grid during high peak time. So taking it during a low peak time, putting it back into the grid during high peak time before we actually put that battery in for recycling. Otherwise, it would go directly from the vehicle to recycling. So when we look at that, the grid right now is getting renewables, clean energy from both nuclear, CO2 free from nuclear, and wind and solar. And it's also getting fuel, and we'll say natural gas. We'll try to ignore the fact that we still have a bit of coal in Ontario. Right? So what we're really looking at is the motivation is that we're going to see a lot more plug-in electric vehicles in the future, a lot more electric vehicles. We're going to see the powertrains are going to have large battery packs. And there's a significant investment in that battery pack. So the battery pack in the Chevy Volt runs about $20,000 right now. So they're quite expensive. So repurposing the batteries employed in these vehicles into a second use, we get more value out of the actual manufactured products. And when it's actually in the electric vehicle, or if it's in the plug-in hybrid electric vehicle, it's only going to contain, once it's lost about 80% of its initial capacity, that's when it's going to come out of the vehicle. And that's based on customer demand. So when I can only get 80% of my original range, I'm going to want it out of my vehicle, and I'm going to want new batteries in there. And that's where the stationary application, such as renewable integration, grid systems, auxiliary systems that require low energy, come into good candidates for these spent electric batteries. They still have good capacities in those applications. They just aren't good for vehicles anymore. So I'll come back to this, but just tell you what we mean by cascaded use. So originally you'd take your battery, you would manufacture your battery, you put it into your vehicle, it would have, at its end of its life, you would actually send it for recycling, and then you would have to remanufacture a new pack. What we're taking to do is that when we have the loop, when it comes out of the vehicle, we're going to put it back into its second use, which is secondary energy storage and stationary application. Use it in that storage before we bring it back in for recycling and put it back in there. So we're actually reusing a product that has already been manufacturing. Now the advantages of this is that if you look at the competition, so you have an internal combustion engine. When I put in gasoline of internal combustion engine, over a life of a vehicle, which is about 8 years, and then we're saying about 10 years life in a secondary application. So if I have an internal combustion engine, I'm going to generate a certain amount of carbon dioxide by burning gasoline over the life of that internal combustion engine. And then the second use, we're saying that, well, power is probably coming, peaking power is going to come from natural gas plant, and the natural gas plant is going to generate a certain amount of CO2 over that 10-year life. Whereas if I have a plug-in electric vehicle, I'm going to get a significant amount of range of that electric vehicle out of pure battery. So I'm going to get a significant amount of that range coming from clean energy, from renewable, charging it at night from either renewables or from nuclear. And so it's going to generate a lot less CO2 than the internal combustion engine here in the red. So my plug-in hybrid vehicle over the life generates a lot less CO2. Then I'm going to repurpose it and put it into the secondary application where it's going to take clean energy at night from wind, solar, nuclear, and it's going to take that clean energy at night, and it's going to offset peaking power, which is probably going to have come from natural gas. So you're seeing it's going to have significantly less CO2 generation because I'm using CO2-free energy. This is sort of the ideal system. What we're trying to do in the research is that we know that over the life of the battery in the vehicle, in the blue here, it's going to have some degradation. So it's going to lose some of its capacity. But one of the things that the car manufacturers don't worry about is they don't worry about what's called charge efficiency. Not only is it going to lose capacity, but it's going to lose its charge efficiency. From an automobile point of view, when I charge up my car, I plug it in at night. As long as I can get my 60 kilometers out of it, that's what I care about. If it goes down to 55 kilometers, that's not so good. 50 kilometers, it's no longer any good for me. I start taking it out of my vehicle. So what I really care about is how much range I can get out of my vehicle. But in its secondary use, what we care about is its charge efficiency. So if it's got 80% degradation in its capacity, it may also be losing some of its charge efficiency, meaning the charge efficiency, how much energy we put into the battery versus how much energy we get out of the battery. If the charge efficiency also degrades down to about 80%, round trip, we're at about 60% round trip efficiency. So in the secondary use application, that starts to become very, very important to consider that battery degradation. So what our research is looking at is we're looking at the cascaded use over the life cycle and the environmental impact over the life cycle of the batteries. So we're trying to see really what is the CO2 gas emissions. We're using that as our metric for all the emissions that we have. And what are we looking at? The performance factors such as capacity fade, charge efficiency fade, charge discharge profiles on the entire grid. And finally, to see what is going to be the impact of these batteries as we put them into a repurposed application. So where do we see them actually coming? Well, if you put them into a residential application, you're going to need 1 to 2 second use EV batteries. When I say EV batteries, I'm talking about the batteries. So that's taking the entire pack out of a vehicle, and you're going to need about 1 to 2 of them in your home to run your home. Now, people say, well, why don't you take apart the battery packs? Well, we've actually done that in our lab, and believe me, once they're together, you don't want to be taking them apart, okay? That's not going to be happening. We're going to be reusing them as a pack, just because of the effort it takes to actually take them apart. So this is a potential application residential. Commercial, office building, grocery stores, especially if you look at stores like food processing, distribution centers that have large refrigerators, have large energy demands, and they can manage their energy demand over the hours. They might be able to develop an application that is 15 to 50 second use EV batteries based on the load profile that they have. So you're looking at a couple, 2, 3 trailers in their parking lot to actually power their commercial application. Where people initially thought that this application would be is that they would put them with the renewable energies. They put them with the wind or the solar sites. But in these applications, they're going to need 500 to 1,000 EV batteries. That's a lot of batteries. That's a lot of storage. And we don't envision this application actually taking place. Just there's not that many batteries coming out of the system right now. There won't be for at least another couple decades. And so we see the first 2 applications being much more applicable. So that's my 7 minutes to talk. But I'm going to steal Jaitan's throne here for a minute, and I'm going to get the discussion going on energy storage. So this is actually from one of the national labs. When they talk about all the different energy storage applications, you see pumped hydro, compressed air, different types of batteries, lithium-ion batteries here, some of the older batteries, lead acid, nickel cadmium, and some of the supercapacitors here. Down here you see how big the energy storage applications could be, and here how long you could be storing the energy. So what you start to look at from energy storage is you say, well, all of the storage application that they looked at in the national labs, they're really storing them for hours, not even a daily storage, right? Whereas power to gas, which was introduced by Rob earlier on, has a real advantage in that not only can I store it for hours and daily, I can store it weekly, I can store it seasonally. So power to gas has real advantages over us and high energy densities. So it has some real advantages. But now the same diagram where I'll raise a little controversy here to get our discussion going. Pumped hydro is great if you have the right geography, right? But it's very limited that we have that geography. Compressed air, geographically limited once again, low energy density, low durability. Personally, I just can't envision these giant silver bags at the bottom of Lake Superior, right? Just can't envision that, right? What Dr. Chen presented, excellent technology, super high energy storage that you're going to get out of zinc air, flow batteries, some of the other new technologies that's coming on, right? And Dr. Chen's making real advantages, right? You might see his technology commercialized in 10 years. It's really, all these technologies are a long way away from being commercialized. Lead-acid lithium-ion batteries, they're there now. And you say, well, why don't you use brand new lithium-ion batteries for energy storage? I will, but remember, that battery pack in my vehicle costs $20,000. You're not going to be using that battery pack to make toast, right? It's there. But when it comes out of my vehicle, what's it worth? It's salvage, it's scrap. I might even be able to be paid to take it off their hands. So it's very low cost repurposing batteries. And then there's the other application that Rob Harvey talked about, which is really auxiliary services. It's not really energy storage, it's the much more short-term solution. So where does that leave our discussion? Well, in Ontario, we've got a congested electrical grid. Pumped hydro, yeah, Niagara Falls is good. We could spend $900 million and build a giant tunnel and have a good pumped hydro storage, but that geography is limited. The cost of battery energy storage is still extremely high, lithium ion. It just hasn't come down yet. So we have that. Vehicle battery packs are now starting to come out of service. So we have plug-in hybrids, and we're starting to see those vehicles coming out of the service. And if I want to move energy around Ontario, it's actually better to move it in the natural gas pipelines than the electrical grids. It's low cost and very, very efficiency, and that infrastructure already exists. We have energy storage infrastructure that might become underutilized. We have pipeline infrastructure that leads to almost all of our homes. So what we really want to do is look at what I call the value proposition. Short-term, daily storage is good for the end user. If I own my building, I care about there. The producer likely is selling his power at a regulated price, so he probably doesn't care so much about energy storage. So energy storage in the short term is probably going to be driven by the regulator, right? So power to gas has a real advantage, and then it offers us transition technology to ultimately the hydrogen economy. No matter what people say, all the car manufacturers, all the OEM manufacturers, GM, Chrysler, Toyota, they're all bringing on board fuel cell vehicles, and they're all going to be commercialized in 2015 to 2017. And yes, they're going to be limited penetration in Southern California, but eventually they're going to come everywhere. So it is eventually coming, and power to gas offers this excellent transition to start to generate some of the hydrogen for that. So what do I say? Short term, if I'm the daily user, I own my building, I own my grocery store, I want backup power, I can buy cheap power at night and use that power during peaking when it's really expensive during the day, but that's right on my site. If I want to move it around long distances, if I want to save it for a week or a term or a longer time, I'm going to need power to gas and biogas transported via the existing natural gas system. So there, I stole your thunder to get your discussion going. How's that?
Thank you. We could count on you to take some actions that would allow people to press the eject button on you. Apologies. We have time for questions. Thank you, Mike, for setting us up with some controversial remarks. So I will remind myself to repeat the question just for recording purposes. Any questions from the audience? Yes, please.
How large exactly is natural gas pipeline? Like when you say seasonal, can you literally store enough power to say for the winter season, in case half an hour to actually be going to the highway season? How large is that?
I will repeat the question. So the question is, how large is the natural gas pipeline? Give us a sense of the magnitude of what amounts of power you could store. Is that the question? Yeah.
Yeah, in Ontario. It's okay. In Ontario, it's 80 terawatt hours is the storage in our natural gas system. And the actual, where the storage come from, it's in southwestern Ontario. Union Gas and near Sarnia and Enbridge have facilities. And it's former natural gas wells. Think about Petroleum Ontario, first in North America, we had significant but limited natural gas in the province, and that's now being repurposed as gas storage and has been since the 1930s.
So to translate 80 terawatt hours, Ken, correct me, Ontario's in a year consumes 160 terawatt hours. Annual energy consumption, 155, 60. It's been around that for the last 3 or 4 years. So fairly big magnitude. Any other questions? Yes, Jonathan.
Yeah, I have a question about power to gas. Wondering about conversion efficiencies, and also in terms of to the hydrogen, and then also what's happening with the oxygen
Okay.
that's being produced. And the other question I had was, you're talking about 1%, 5% hydrogen in natural gas. Where do you get the problems with equipment where there's too much hydrogen?
Okay, I'll repeat.
If there's such a limit?
I will repeat the questions. The question is, can you clarify what is power to gas, role of hydrogen, energy conversion efficiencies, and what sorts of limits around whether it's 2% or 5% and why?
All good questions. The conversion efficiency from electricity into hydrogen is in the 79–80% range for electrolysis. And in terms of the proportion of hydrogen in the grid, you're right that there are limitations on how much hydrogen you can inject. There's been a lot of research done with GERD, which is a EU gas association, and also the Gas Technology Institute of Chicago, and they feel that 10% is a practical limit for hydrogen. The issue, if you're not aware, the issue with higher concentrations, that would probably be concentrations over 15 or 20%, is a risk of embrittlement with the pipeline infrastructure, and more importantly, the end use. So at the burner tip, the characteristics of the flame, if it were for a gas range at home, for example, or something like that, you begin to have issues if you get into the 15 and 20%. So 10%, but 10% of 80 terawatt hours would be far more than probably we'd ever need.
Thank you, Rob. Yes, John?
You had an earlier presentation about the water intensity of various forms of energy, coal, nuclear, and some things. So on the electrolysis, how much water do you need? What is the source of that water? Do you need fresh water?
Let me repeat the question. Question is related to the use of water consumption. Previously, we had a presentation which gave you a certain sense of different energy options and how much water is consumed to produce the energy. The question here is, if you're going to use hydrogen, electrolysis is the process. Can you give us a sense of the usage of water for this process?
Usage, it's 9 liters per kilogram of hydrogen, and that's basic chemistry, the stoichiometric values for that. You saw the container. We didn't show inside the container. The turnkey electrolyzer system that Hydrogenics provides includes the stack or the electrolyzer itself. It's also got the balance of plant, which includes rectifier and a water treatment. So basically, where these are installed in on-site generation in industrial applications, they're basically taking tap water, city tap water, and then you're deionizing the water. And there may be some other water treatment depending on what's required in that particular location, but that's what we use.
There is a need to clarify what one calls consumptive use of water, and people say nuclear power plants consume water, and yes and no. Yes, in the sense that there is some consumptive losses, but a lot of the water is recycled back into the river because they go through the condensed cooling water systems. Can you help shed some light on that with respect to electrolyzers? I guess that's strictly consumptive
That
use, right?
Depends how broadly you're looking at the cycle. If you look at it, it would be strictly consumptive on site to produce the hydrogen. I didn't mention there's also a question with the oxygen. Usually the oxygen is vented. If you happen to do this near a wastewater treatment and there was some application where you could use the oxygen, then I think there's a few places in the world that's been done, but usually it's vented. So it is consumed at that point, Jatine, but when the hydrogen, if it's in a fuel cell electric vehicle, you're producing water again when that hydrogen is combusted. So I don't fully know enough chemistry to know exactly the answer to that question, but you do get the water back at some point.
Okay, thank you. There were a few other questions. Yes, Keith?
Yeah, in terms of wealth creation, let's say jobs for our students, how much manufacturing do you see going on in Ontario, either now or will happen in the future if it's three different types of technologies?
The question is the potential for employment, job creation. What do you see in terms of the options that you outlined here?
The next generation electrolyzer, the PEM electrolyzer, has been designed and developed in Mississauga, and our facility there, and would be manufactured there as well. It's always risky trying to hazard a guess in terms of manufacturing jobs from that. But if you look at again, Germany is looking at 1,300 megawatts of capacity for power to gas between now and 2023. So you think about how many electrolyzers that involves, it would be significant. We see this as a potentially very large market. And the manufacturing for those electrolyzers and balance of plant would be done here in the GTA.
That's excellent.
Thank you. I generally don't drive through red lights, but often go through for 5 minutes if the questions are there. So we will do so. If there are a few more questions, we can entertain
How
them.
about the other two technologies? Where do they see in terms of
I'll comment on lithium-ion batteries. Right now, lithium-ion batteries you see in your vehicles, 99% of the production is in China, Korea, or in the Asian countries, the original battery itself. But the repurposing would stay here, and the recycling could be here, right? So the original battery is already being manufactured. Zhang, where are you going to build yours?
So the answer there was there is some part of the value chain when you repurpose the batteries, and it takes you up to a certain spot.
Yeah, for our technology, as I mentioned, we say it's the next generation battery technology. So if it is successful, I think the battery market is already there. It's billions of dollars. So it really depends if this technology really can meet the cost and the lifetime and the performance of the battery of the market.
Would you like to take up Professor Fowler on his challenge? There is not going to be 10 years to cycle. It actually will be 2, because our graduate students are so smart and they'll figure out the issues.
I believe with the time you will see this new technology in some market first. Then maybe, if it is really good, maybe you can replace the current, a lot of current, like a lead acid battery, lithium battery technology market. That's my feeling. Yeah.
but we're really manufacturing?
I think for this new technology battery, because for the manufacture, it's more related to the technology and less human labor. So I believe it should be located in Canada or North America.
Thank you. There's one more question? There's 2 actually. Yeah.
Considering Canada is one of the top 5 zinc producers, so components of that battery would be manufactured in Canada.
So the observation from the audience is that Canada is one of the largest producers of zinc, right? But you had a question? No. One more question?
Yeah, a quick comment on that. However, zinc co-occurs with lead, so you're increasing lead production if you're increasing zinc production, geologically. But one thing that Harvey mentioned in passing, and I thought it might affect the other technologies too, is even though the technologies may be there or coming, I think one of the bigger barriers to implementation is ultimately standards and regulation around security and safety and those sorts of things. So repurposed batteries, are there going to be hurdles? And our natural gas system is quite sacred. Are we going to be allowing people to stick other stuff into that system.
So if I'll just paraphrase your question, the question is technologies and their development status, even if you assume optimistically that they're either there or will be there soon, there are other barriers, and they relate to standards development, regulatory and other financial aspects. So perhaps some of you can comment on those aspects.
Yes, you're absolutely right. I mean, if we had approvals today and could start our project today, injecting hydrogen into the natural gas grid, there are no standards for it whatsoever. I mean, it's important on the demonstration project, and that is one of the key objectives of the demonstration project. In the fact that they're doing it in Germany on a demonstration basis doesn't carry any weight here in Ontario, nor should it. You know, we're partnering with the Canadian Gas Association and ETIC, our partner on this demonstration project, and that's one of the standards. We're also working with Mike Fowler's group and the University of Waterloo for research in terms of the hydrogen in reservoirs, and that would be part of the learnings and research that would use to craft standards, interoperability standards.
One more question? Yes, Mel?
Well, more of a comment. In Ontario, the natural gas system for the last 10 years has been flat in terms of demand, because even though we're bringing new customers on, energy efficiency is actually taking off more than what the new customers are demanding. So we're always looking for new opportunities to carry product like hydrogen with the natural gas stream, because ultimately we see actually the capacity declining over time in those pipes.
Yeah, I'll paraphrase that observation. So Mel is indicating that over the last little while, the natural gas demand has been relatively flat, partly driven by improvements to energy efficiency programs and so on. So now there is this opportunity, in light of a lower demand, but the infrastructure is there, to repurpose is perhaps the wrong word, to be able to seek other opportunities, and power to gas, hydrogen in the gas system is one aspect thereof. Okay? So we don't have to build new infrastructure to accommodate that. Perhaps one or two last questions, if any. Yes, John, and let me go to him first and I'll come back to you. You had raised your arm before, sorry.
I was just wondering about the water aspect of the hydrogen. Couldn't that potentially in the future affect our fresh water supply? We had mentioned that there were ethics involved in using food crops for ethanol generation, but what about the ethics of using our fresh water supply for hydrogen generation?
Okay, good question. We talked about water again. We'll come back to it. The question is, just to sharpen it up a bit, so the implications of water usage for, let's call it, larger scale implementation of a hydrogen solution as part of the energy equation that we're discussing, and criticisms have been made about water usage for biofuels through ethanol. Will hydrogen take us there as well, or no?
So I can do this. We've looked at this. This research has gone on with fuel cells for a number of years, because I looked at hydrogen being produced for fuel cells being used. Yes, you're going to use clean water for fuel cells, and you're going to produce that hydrogen with clean water in the region. But then that water doesn't leave your region. It drips out of the back end of your vehicle. So literally you're going to have your electrolyzer in Sarnia, and the car that's driving from Sarnia to London is dripping the water all the way along the highway. It's actually not dripping it, it's coming out as vapor. So what you're doing is you're transporting, you're just increasing a small amount of the transportation of the water out there. And we've looked at this with hydrogen vehicles, and if we converted all the vehicles in North America to hydrogen vehicles, it turned out to be a small fraction of a single city use of water. The amount of water that's actually used is really negligible.
So the observation is that it's, from an ecosystem loss standpoint, it's a net, it's not going to be an issue, or at least that's Professor Fowler's view. Yes. There is one, and then I'll come back to you, John.
Some Asian countries, the energy-starving countries are those countries which are unable to produce enough energy. So instead of storing energy, the energy can be spent in such countries, and then these countries which are supplying energy, they can have the power plants in those countries. Because in India, a lot of solar energy is there, but then they don't have enough infrastructure in making use of the solar energy.
So,
instead of storing energy, you can supply energy like any other commercial commodity, and then get back, if not money, get back energy from them by establishing power plants in those countries.
okay, if I get your question right, I'll try and summarize, see what I think I heard, that there are countries where energy supply is a problem. So rather than storage, which seems to be the focus here, what you're saying is why not provide the technologies to create the supply in countries like India or other parts of the world, and bring back the
energy.
back. Okay. Anyone wants to take that on, or I'm not clear of the question myself, to be quite honest.
Like in India, that in major cities, 6 hour or 4 hour power shortage is there, where power will not be available in major cities.
Okay. Power shortages
Yes,
in India
so
is.
where power is stored here, instead of splitting there where it is required.
Aha, that's, if I know, we could pull magic by just taking stored power from here and meet the demand upsets in distant countries, I think would be a challenge. But again, we have to think about that, whether it's feasible or not. I would like to perhaps end, John, one last question.
Just a quick question for Dr. Chen. So on the zinc air battery, so we know the zinc is plentiful, but is there limits? Are you using rare earths in that battery, or are you using nano manufacturing, which you still have a very high cost, and you have to bring that down to make that commercially viable? That's a very good question. Actually, for the catalyst, we developed the amount that we use in the battery. It's first, it's very tiny. It's a milligram per centimeter square loading, so loading is very low. And the cost at the current stage, compare with, for example, like current other technology, like a fuel cell, the other area using precious metal catalyst, the current our cost is very low. And also, in our lab, definitely it's still, when we prepare the materials, it's still in small scale. But in terms of the procedure we are using to prepare the catalyst, the scale up, it's actually kind of very easy. So it's, with the time, I believe, this will not be a problem. That's my feeling. Yeah.
Thank you. I think on that note, 2 or 3 observations I would now like to formally bring to a close, certainly this session and of course the Energy Day as well. To the audience, very many thanks for your participation, and I hope this has been a useful and enlightening day for you, and you will have the desire and courage to go look things up on our website to see how much more or the scope and scale of energy research underway here at the University of Waterloo. If I may ask the audience to take this opportunity to thank our panelists for their thoughtful remarks. Thank you very much for your participation. Bye now.